In this video, we'll look at quantum theory and the nature of light. Before we start talking about light, we first want to look at the electromagnetic radiation. So to understand the electronic structure of an atom, we have to understand the nature of what electromagnetic radiation is. Electromagnetic radiation is characterized by its wave nature. And so when we display an electromagnetic spectrum, it's usually displayed as various types of radiation in order of increasing wavelength. And so an example of an electromagnetic spectrum shown here, we can see that it's arranged from a smaller wavelength going up to larger wavelengths. And so smaller wavelengths would be our gamma rays, followed by X-rays, ultraviolet, the visible part of the spectrum, infrared, microwaves, and radio waves. And then you can see the frequency gets larger. And so when we're looking at our wavelength, we usually write it as lambda, and our frequency is written as kind of a V. And we can see here that the wavelength is going to be inversely proportional to the frequency. So the larger our wavelength gets, the smaller our frequency is. The larger our frequency is, the smaller our wavelength. We can see the visible part of the spectrum is a really small portion of the entire electromagnetic spectrum. And this little portion here encompasses all the light and all the colors we see in the world. And if we think about all the colors we see in the world, most people can see about 10 million different colors. And all those 10 million different colors encompasses just this small portion of the electromagnetic spectrum. It's just this tiniest little portion is what we can see. There's all the other parts of the electromagnetic spectrum that we can't see with our eye, but we can pick up with different instruments. And so you'll see a lot of pictures from NASA looking at different galaxies in different wavelengths, and then they color it to adjust it so we can actually see it. And so the visible light we see, that's a form of electromagnetic radiation, or you can also call it radiant energy, if you want to use a fancier term there. The electromagnetic radiation, it travels at the same velocity of the speed of light. So our electromagnetic radiation and light both travel at the same speed, which means our electromagnetic radiation travels at roughly 3.00 times 10 to the 8th meters per second. If we know the speed of light and we know what our wavelength is, we can calculate the velocity. So we have our speed of light equals our wavelength. The inverse proportionality of the wavelength and velocity allows us to use those two in our equation here to multiply by the speed of light. Since that is our constant that's fixed, everything travels at that same speed. Let's look a little bit more at this actual wave property and the wave aspect of the electromagnetic radiation. If you think about a wave, let's say you're on the beach, you watch the waves roll in. The ocean has waves that roll in kind of in a predictable pattern. And when you're looking out at the ocean, you can see the wavelength is going to be from the top of one wave to the top of the next wave. Or you can also say it's from the bottom of one wave, the trough, to the trough of the next wave. Both of those would be the wavelength, because that's how much distance is in between that wave. So now let's say you're a surfer, or maybe you're just watching the surfers because the water's too cold. You see the surfer sitting there in the water, and the waves are rolling past them while they're waiting for the turn or they're waiting for the right wave before they can go surf it. The amount of waves that roll past within a minute, that could be the frequency. Or the amount of waves that roll past within a second, that could be its frequency. So how many waves go past that surfer in a given time represents the frequency. Same thing with our wavelengths for light. If we look at a fixed position and see how many wavelengths go past in a given time, usually per second, that becomes our frequency. So our unit for wavelength, you can, if you remember, was meters. And our unit for frequency is per second, so it's 1/seconds. And then so now we've looked at the wavelength, the distance between the tops of the wave, we looked at the frequency. Last thing we want to look at is the amplitude. The amplitude is how high your wave is. Let's say we're that surfer again. During a storm, you might have really large waves, or if you go out to Mavericks, the waves are really big. They have a really large amplitude. Or let's say it's a nice, calm, sunny afternoon. The waves might not be that big. You might not see the ocean really move at all. So they'd have a really small amplitude. And the same idea applies to light. The higher the amplitude, so the larger the wave, just the taller the wave is, the brighter the light is. Or the smaller the wave, the dimmer it is. You can almost think of it as using like a dimmer switch on for the light in your living room. Same idea here. If we use a dimmer switch, you can make the wave taller or we can make it smaller. But the frequency and the wavelength don't change. So we can see here between the tall one, that wavelength is the exact same as between our shorter waves. So they both have the exact same wavelength there. The only thing that's changed is the height of our wave. And so now looking at all of this and looking at wavelengths of different colors. We can see here on this page, all the different colors we can see with our eye. The human eye can usually see from about 400 nanometers all the way up to about 750. So some of you guys might be looking at this and saying, I can't even see the violet here. So you might not be able to see that low on the spectrum. Or other people might be saying, I can't see the dark red. Some people might not be able to see that high on the spectrum. So that 400 to 750, that's where most people see. Some might not see the really low ones. Some might not see the really high ones. And if you happen to be colorblind, you might not be able to see all these colors correctly. So that's why it's also labeled with the color name. So our violet ones, those you can see are our shorter wavelengths. They have a much shorter gap between the two crests, or we'll say the two troughs. The indigo, the next one, you can see it gets a little bit bigger. And then with the blue, you can see the wavelength gets a little bit bigger each time. So this 400 nanometers, that's the distance here, the distance between the two waves. Or even if we go all the way up to the red, the 700 nanometers. Or the dark red, I should say, the 700 nanometers. That's going to be the distance between the two troughs here. So you can see it's much longer of a distance between the two tops of the waves here versus the blue or the violet. And so it's this length of wave is how we detect the different colors. That's the difference between all the colors we see is what wavelength it is. And so now that we know a little bit about wavelengths and light and the electromagnetic spectrum, let's start looking a little closer at the actual energy of the light. And for that, we're first going to start with the Planck constant and Max Planck. So Max Planck was a scientist and a physicist in the late 1800s. He discovered that energy couldn't take any value it wanted. So energy wasn't actually continuous. Instead, the energy is quantized. It occurs in fixed amounts. And so he called this fixed energy a quantum. And the quantity that Max Planck described is what we now call Planck's constant. And he figured out the relationship between energy and frequency, where you have E equals energy. So our energy equals our frequency times his constant. And so you can see Planck's constant, which we usually write as an H, is 6.626 times 10 to the negative 34th joules seconds. The unit of joule is a unit of energy we have, so we call it a joule second. And so according to Planck's theory, matter can emit or absorb energy only in whole numbers of this multiple. So our energy can equal hv, or can equal 2 times hv, or 3 times hv, or 4, but it can't be like 2.1 times hv. It has to be a whole number. And we can think of that as like we're walking up stairs versus walking up a ramp. So if you're walking upstairs, you're walking up discrete steps. You can almost think of this as the discrete lines of energy that the person is walking up, versus having something as a ramp, which is continuous. You can put your foot wherever you want on that ramp, but on the stairs, you can't put your foot anywhere you want. Meaning you can't put your foot like halfway up the stair and expect to be able to walk on it. Instead, you have to put your foot on the top of each step. So it has to go in a very particular spot. So this would be more like our quantized energy. And this side would be more of our continuous. So Planck showed us that energy has to be quantized like this. And the gap, so you can think that the height of each step, that's the gap. That's the Planck's constant. So that's 6.626 times 10 to the negative 34 joule seconds. That would be the height of each step there, or the height of the difference between each energy level. And then this takes us to our next physicist and our next thought and process about the nature of energy, which brings us to Einstein. Everybody knows Einstein. Einstein assumed that light had to travel as energy, and he said that energy traveled in packets. And so just like how Planck said energy had to be quantized, it had to be a certain number, a certain amount, Einstein decided, well, if it has to be a certain amount, maybe it comes as a packet. And that packet is what he called a photon. So the photon we can think of is almost like a particle of energy. It's a little packet of energy you get from light. And you can think if we look in the sun, when the sun does its fusion, it will start emitting light as radiation, and the electromagnetic radiation, that's the light we see. Those are the photons. It emits it as photons for a visible light. So I said a photon is a quantum of the electromagnetic radiation, which means the electromagnetic radiation is actually itself quantized. It comes as only certain amounts. And we can see this when we look at what we call the photoelectric effect. With the photoelectric effect, electrons are emitted when the frequency of a radiation is above a minimum threshold. So what does that mean? If we have light of a certain frequency, so a certain amount of waves per second hits our object, nothing would happen if the wavelengths are too long. So if the energy of that wave is too small. Let's say once we get a frequency that's close to the threshold of our material, like with visible light for an example, when visible light would hit our surface, it's going to excite and release an electron. And then anything above that has a frequency that's high enough to release that electron. So with our visible light, the electron gets released. Anything that's a higher frequency, or anything that's a higher frequency, that will release an electron. So if visible light does it, ultraviolet light will, X-rays will, and gamma rays will. And it's this idea that we use for solar cells and solar panels. The light from the sun will hit the solar panel, and if it hits it at the correct wavelength, the solar panel will release an electron, and then we can use that electron for electricity. It's a lot more complicated than that, but that's kind of the gist of how solar cells work. And so looking at this nature of energy, he used this assumption to explain this photoelectric effect. He used the quantized idea to explain the photoelectric effect, where we'd have radiant energy hits a metal surface. If it's the correct amount of energy or higher, the surface in the metal will start to lose electrons. And then if your surface of metal starts to lose electrons and you attach it to a battery, you can actually get a current. And so Einstein concluded that the energy is proportional to the frequency. So our energy equals Planck's constant times the frequency. Notice how Planck's constant is still in there. The energy is quantized according to Planck's constant. And so if you know the wavelength of a light, you can calculate the energy of a photon. Or we can call that a packet of the light. So if we know the speed of light equals the wavelength times the frequency, and I know the energy equals Planck's constant times the frequency, we can convert both of those to have our frequency equal energy over Planck's constant, or in our second case, our frequency equals our wavelength over the speed of light. Combining those two equations together, we can get energy equals Planck's constant times the speed of light divided by lambda. So that means our energy is always for any wavelength or any photon. So we can figure out the energy per photon this way too. Our energy equals Planck's constant times the speed of light divided by the wavelength. And so now that we know a little bit more about the nature of the electromagnetic spectrum, the nature of light, the quantization of light, and the photoelectric effect, let's practice a few problems and practice some of these equations. So if we have the yellow light of a sodium lamp, which has a wavelength of 589 nanometers, what is the frequency of this radiation? Well, we can think we're asked frequency, V, we're given a wavelength, lambda. An equation we can use to solve for this is speed of light equals lambda times the frequency. And we choose this equation because we know the speed of light, we know the wavelength. So our other equation that contains frequency, energy equals hv, we can't really use that one because we don't know what the energy is. So this is an unknown and this is an unknown. Here, I know what the speed of light is. I know what lambda is. I just need to solve for v. So that means v equals speed of light over lambda, which would equal 3.00 times 10 to the 8th meters per second divided by 589 times 10 to the negative 9th meters. So it's easy to, this is an easy way to convert between nanometers and meters. Take your number for nanometers times 10 to the negative 9th equals meters. This way my meters cancel out, and then you're just left in inverse seconds. So once we calculate that, we end up with about 5.09 times 10 to the 14th inverse seconds. And so that means the frequency of our yellow light is that 5.9 times 10 to the 14th inverse seconds. So now let's take this idea a little further. Let's say we want to calculate the energy of one photon of the yellow light that has a wavelength of 589 nanometers. So now you can see we want to calculate energy, E, and we're given a wavelength, lambda. So for something like this, we're going to want to use our equation, E equals Planck's constant times V. But we don't know what V is here. Oh, we forgot to write it down from the previous problem. So E is going to equal h times the speed of light divided by lambda. So now we have everything in our equation here that we need. So we're going to plug in h, our Planck's constant is 6.626 times 10 to the negative 34th joule seconds. Our speed of light, that was 3.00 times 10 to the 8th meter over seconds. When we do it this way, our seconds will cancel. And that's all divided by the wavelength. And we remember our trick, we have 589 nanometers, so that's 589 times 10 to the negative 9th meters. So this way meters cancel. We plug all of that into our calculator. So this means the energy of one photon is 3.37 times 10 to the negative 19th joules. Not very much energy per photon, is it? But remember, you have billions and billions and billions of photons going all the time. So the individual photon may not have much energy, but collectively, that's where they have a lot of energy. So now we've seen a little bit about the nature of light, how to do a couple calculations for wavelength and energy and frequency, and how to relate those three together. We've also learned about Planck's constant and how energy is quantized according to Planck's constant.